Hello, welcome to the next section, more list algorithms. We'll begin with binary numbers, then we'll wrap this section with a look at greedy algorithms and backtracking. Now we move on to the first video of this section that deals with binary numbers. This video deals with the operations pertaining to binary numbers. Here we'll add and multiply binary numbers. We use a list int to represent binary numbers, a list of zeros and ones. If you pass in a list that has any other numbers except 0 or 1, the algorithms will throw an exception. We'll first take a look at handling the carry operation. For example, when you add 1 to 1011, decimal 11, you get 1100, decimal 12. Here is how a carry is propagated. Before we try modelling the binary numbers as a list, there's a caveat we need to be aware of. We write a binary number from left to right. In other words, the most significant bit is at the leftmost, and the least significant bit of a binary number is at the rightmost. To add a carry, we typically start from the right. However, as we've already seen, for a list, that would be the tail. Working on a list tail is expensive. Instead, we want to work at the head of the list and express operations using list prepend. This means we need to reverse the list, so we can both work at the head of the list as well as start operating from the LSB bit onward. With this under our belt, here is the carry operation. We first define the carry method. After this, we enter our first clause. When the carry bit is 0, there is no change, and we return the list as is. The next case is when the carry is 1 and the list empty. The clause just returns a list that has 1. The third clause has carry as 1 and a non-empty list. Let's say x is 1. If so, then we'll have 0, and the carry will propagate to the rest of the list. We'll now enter the final clause, and this is used to catch mistakes. For example, if we erroneously send a list with the digit 2, the clause catches it and aborts the program execution. This is a helper function used in the summation function, and these are the 4 clauses. Let's exercise it. This is the code for doing it. As noted, the number is 1011, and adding 1 to it, we get 1100. We work on it in reverse fashion, so we can express operations on the LSB in terms of list head operations. Let's try adding 2 binary numbers. For example, adding 01011, that is 11, to 11110, that is 30, should give us 41. We use the carry helper method to realize the addition. This figure shows the addition of binary 11110, decimal 30, to binary 01011, decimal 11. Adding the second bits, from the right, generates a carry that keeps propagating. The addition results in 41. Let's now look at the add method. The carry bit is initially set to 0. Here we match the pair formed by both the lists. If both the lists are empty and the carry bit is 1, we return 1, and if not, we return 0. We'll now push the latter part to the carry method. This case is triggered when the first list is empty, but the second is not. In this case, we just absorb the carry bit in the second list and return it. Note this part. We don't really care about binding the match to any identifier. We just need to make sure the list is non-empty. We use the underscore to stress that we don't care about the actual list elements. This case is similar to the second case where the first list is not empty but the second one is. This is the general case where both the lists are not empty. Let's say we have c equals 1, x equals 1, and y equals 1. The addition leaves 1 behind, and the carry becomes 1. We propagate the carry along the rest of the addition. Working out the rest of the cases is left for you as an exercise. We could improve the interface a bit, as sending an initial 0 for a carry is really part of the implementation detail. We'll now look at the addNums function. The addNums function in turn calls add. It hides all the list reversals, so the usage feels more natural. Let's look at some examples. Here, the first list is 1 and 0. The second list is also 1 and 0. When we add them, we get 100. In the same way, when we add 1011, with 11110, we get 101001. We'll now learn about the multiplication method. This is the code to do that. We first define a multiplication list. Then we hide the reversal process using an inner method called multiply. When we run this, we get this output. As shown, the multi-method takes two lists, each made up of 0 and 1. The first clause is simple. If the left operand is empty, we return an empty list. There is just nothing left to multiply with. The second case is when the current bit is 0. This does a bitwise left shift. This diagram shows the case when the current bit is 1. The third case is when the current bit is 1. In this case, we just add QS to the result of multiplying XS and QS. This figure depicts this clause properly. Multiplying two binary numbers is just a little more elaborate than the process of adding them. Multiplying is repeated addition. For example, multiplying 1111 decimal 15 with 11 decimal 3 gives us 101101 decimal 45. We just add 1111 to itself twice. This figure shows the actual operation performed. Here, both the operands are bits, and they are 1. What happens when they are 0 bits? For each 0 bit, we shift to the left. It might help to remember that when we multiply a number by 2, binary 1, 0, we do a bitwise shift left. This diagram depicts the process when we multiply the binary 111 decimal 7 with the binary 101 decimal 5. The result is 35. In this video, we learned about binary numbers operation. Great!